Today's topic is logarithmic functions. So what is a logarithm? Well, let's review inverse functions really quick. So say we have the function y is equal to 3x plus 2. Remember that this is the equation of a line, and this line is 1 to 1, and it's 1 to 1 because it passes the horizontal line test, which tells us that we have an inverse function for this line. And how we find the inverse function is we take this line, which usually we have it written like this, f of x is equal to 3x plus 2. But what we're going to do with this is we're going to switch x and y. So now we say x is equal to 3y plus 2, and we solve for y. So we move the 2 to the other side, and then divide by 3. And so this is the inverse function, and we usually label it as f inverse of x is x over 3 minus 2/3. This function is also a line, and it's 1 to 1. Now, in the last few videos, we were talking about exponential functions. So we had functions that looked like f of x is equal to 2 to the x. And we said that this function, if we were to graph it, it looks something like this. It goes through the point 0, 1, heads up like that, and then this side goes towards this horizontal asymptote, y is equal to 0. This function is 1 to 1, and it has an inverse. So the idea of finding the inverse of this function is very similar to what we did with finding the inverse of a line or any other equation we have seen before. So what we do is we say this is y is equal to 2 to the x, and then we switch x and y. So we say x is equal to 2 to the y. Now here it's a little tougher to solve for y because we have y in a power, and so we want to bring that power down. And doing that, we use something called a logarithm. So what we're going to see is that y is going to be equal to log base 2 of x. So this is how you want to think about it. You have 2, this base was going here, this smaller number that's kind of like in the base. You can think of this being the basement of the log, like down here. That goes with this number here. So this 2 and this 2 are the same. The exponent is out here, and this letter x is right here. So maybe how I like to think of it is it's like you switch this x and this y, and then you stick a log in the front. So you can see if I switch x and y, because this is sort of like 2 to the x in a way. So it was 2 to the y. So now I have the x here. I put a log in the front, and then I have the y on this side. Now we can talk about the graph of the log, and we're going to do that a little bit later as well. But real briefly, remember that an inverse function is symmetric to the original function. It's a mirror image of the original function along the line y is equal to x. So it looks something like this. Now this function went through the point 0, 1, but this one's going to go through the point 1, 0, and this will become the asymptote here. So we'll have an asymptote at x is equal to 0. So this is just a very brief introduction to logarithms. So this equation right here, which is f inverse of x, it's log base 2 of x. So if we have f of x is equal to a to the x, where a is not equal to 1 and a is greater than 0, so it's a real number that's greater than 0 but not the number 1, then the inverse of this function is equal to log base a of x. So let's keep that in mind. So our first step in understanding these functions is to do a few problems just relating exponents to logarithms, just to get some practice. and then we'll do some graphing, and then we'll solve some logarithmic functions and some logarithmic equations. So here I want to change each exponential statement to a statement involving a log. My first problem is 3 to the 4th is equal to 81. Now remember what I said, to change to a log, you switch these two and then put a log in the front. So this is the same thing as log base 3 of 81 is equal to 4. So 3 to the 4th is 81. A logarithm is an exponent. So what you're asking yourself here, if I just gave you this piece here, it's like 3 to what power would give me 81? And that power is 4. So that's what this logarithm is equal to. Whenever we have a logarithm, it's always this power. That's why you get this number 4 on the outside. So right now we're just switching. We're going from logs to exponents just to get some practice. Here's the next problem. 2 to the negative 3 is equal to 1 over 8. Well, if we want to make it into a log expression, this is log. 2 is the base of this exponent, so we put the 2 here, and then we switch these two. So this is 1/8 is equal to negative 3. You don't have to put the parentheses here. I just like to do it so I don't get confused. I'm not taking log base 2 of 1 and then dividing by 8. I just like to put whatever, if it's not just a single number, I like to put it in parentheses like this. Let's try this one. Square root of 5 to the power 0 is equal to 1. So log, here's the base, put that in the basement of the log. This 1 goes here, and the 0 goes on this side. So this is saying the square root of 5 to the power 0 is equal to 1. Now we're going to do the opposite. I'm going to give you a logarithm, and I want to form a statement that involves an exponent. So here I have log base 10 of 100 is equal to 2. So this is the same as 10 to the 2 is equal to 100. So what we're doing is we're switching these two, and then we drop the log. So 10 squared is 100. Here's the next problem. Log base 2 of 1/2 is negative 1. So this is the same as saying 2 to the negative 1 is 1/2. Again, switch these two, and then drop the log. The next one says log base 125 of 5 is equal to 1/3. So this means that 125 to the 1/3 is equal to 5. Switch these two and drop the log. Now let's make sure that we understand what a logarithm is. So we're going to find the value of each of the following logarithms without a calculator. So I have log base 2 of 16. So remember what we said that a logarithm is. I'm going to write it in red over here. A logarithm is an exponent. So what I'm asking, when I ask you for log base 2 of 16, I'm saying 2 to what power gives me 16? So think about that. How many times do you have to multiply 2 with itself to get 16? Well, that's 4 times. 1, 2, 3, 4. So this is equal to 4 because 2 to the 4th is 16. How about this one? Log base 3 of 1 over 27. So again, 3 to what power is equal to 1 over 27? I know that 3 times 3 times 3 is 27. But how do I get 1 over 27? Well, I've got to put a negative with that 3, because then that is 1 over 3 cubed, which is 1 over 27. So this exponent is negative 3. So that's what this logarithm is equal to. Okay, try this one. Log base 8 of 1. Maybe pause the video and see if you can figure this one out. So 8 to what power is equal to 1? Well, remember, any number other than 0, if you raise it to the power 0, you get 1. So this is equal to 0. 8 to the power 0 is 1. All right, now we're going to talk about the graph of a logarithmic function. We discussed it a little while ago, but now we're really going to go into detail. So the first thing I want to draw is I want to draw the function y is equal to a to the power x, where a is greater than 1. Now remember that such a function always goes through the point 0, 1. Because if I plug 0 here, now a is any number, so it could be 2, 4, 100, any number, but if you raise it to the power 0, you get the number 1. And then we know that this function goes up like this, and then it heads towards this asymptote of y is equal to 0. So this is the function y is equal to a to the power x. For a logarithm, remember, the inverse function is always the mirror image of the original function with respect to this line y is equal to x. So this point here, 0, 1, now goes to 1, 0. And let's see if that's true. So what is, now if I let x equal 1, what is log of base a of 1 equal to? Well, remember, this is a raised to what power is equal to 1. And as long as this number is not 0, which we're assuming a is greater than 1 in this case, then we're going to get that this number has to be 0, because 2 to the power 0 is 1. Like that problem we just saw a minute ago. We said log base 8 of 1 is equal to 0. This a this time is just any number greater than 1. So we do get the point when x is 1, we get that this log is equal to 0. So that is our y coordinate. So we have the point 1, 0. So that's why we have this point on the graph. And then this portion of the graph is going to go like this. And then this portion of the graph is going to go down towards this asymptote, x is equal to 0. Draw that a little bit better. Something like that. And you can plug in some more things into your logarithm so to get an idea. Now remember, a is greater than 1. So let's say we plug in log base a. Let's put in 2. What is this equal to? Well, a to what power? So let's put an x is equal to 2. Well, this number has to be greater than 0, because if I put in a 0, I get 1. And if I put something like 1 in, well, that depends on what a is. But it's definitely going to be greater than 0, which is why this line, you can see that this picture of this line is above this axis here. And the bigger the number is, the bigger the number you're going to plug in this power. That's why it's getting higher and higher. Okay? And then if we start plugging in something between 0 and 1, so if we wanted to figure out log base a, let's say 1 over a, that's an example. So if this number is greater than 1, 1 over that number, so if this number is 2, then 1 over 2 is a half, which is halfway between 0 and 1. Well, that would be -1, right? Because a to the power -1 would give us 1 over a, which is why we're going down like this. Okay, so some things to notice about the graph. First off, this graph, so f, maybe I just should say y is equal to log base a of x is 1 to 1. Let's see, it's 1 to 1. If I use a horizontal line, I'm only going to hit this graph one time. This is going up and towards infinity. And it's an increasing function. Sorry. No, yeah, it is increasing. Notice that as x goes towards infinity, as we go this direction, our function is going up along this line. If we were a car on this function, and we're going from left to right, so we would have to go up and then this direction. So we're an increasing function here. What else do we notice? Remember the domain and the range of this function. The domain is all real numbers, and the range we said was 0 to infinity. And you can just look at this graph and see. Domain is how far left and right you go. So you go out to negative infinity this way, and this graph is going up and kind of to the right all the time. So that's the domain. But the range is how far up and down you go. And you can see we're going up to infinity. But down, we kind of head towards this asymptote of y is equal to 0. We're never going to touch it. That's why the lowest number here is 0. Remember what we said about inverse functions. The domain of an inverse function is the range of the original function. And the range of the inverse is the domain of the original. So that tells us that the domain for this function here, y is equal to log base a of x, the domain is 0 to infinity. But we could just look at the graph and see that. You can see, remember, domain is how far left and right you go. You can see that this graph goes up to 0, but it never touches it or goes past it. And then if we go this way, we're going to have points on this line. So 0 to infinity is correct. And then as for the range is how far up and down you go. You can see that as we go down this number line, we're going to have points on this line. So we go to negative infinity. But also as we go up, we're always going to have, even if we go way up here, this thing is going to keep going upwards. So we're always going to have a point no matter how far up we go. So negative infinity to infinity, and you can see that these two are switched. Let's see. The other thing I want to mention is that for the original graph, this green line, we had a horizontal asymptote at y is equal to 0. But now, for our inverse function, we're going to have a vertical asymptote, VA for vertical asymptote, and that is x is equal to 0. Okay, now let's switch this. When we were talking about exponential functions, we did say y is equal to a to the power x, but we mentioned that a was going to be greater than 0, but not equal to 1. So we looked at half the cases when a is greater than 1. Now let's talk about when a is between 0 and 1. So let me erase some of this stuff. Okay, so we want a, instead of it being greater than 0, we're going to talk about the function y is equal to a to the power x when a is between 0 and 1. So let's remember what that graph looked like. Remember that it went through the point 0, 1, but on this side it went up to infinity, and then on this side it went towards the horizontal asymptote of y is equal to 0. So if we want to draw the graph of the logarithm, here a is going to be between 0 and 1. So what do you think this graph is going to look like? Well, it's going to look like this graph. It's going to go through the same point here, but just the mirror image. You see how we have this asymptote here? Well, then if we take the mirror image, we're going to have the asymptote here. And then this portion of the graph is going to go like this. So this is y is equal to log base a of x. Also remember that if we had a between 0 and 1, so let's give an example, 1/2 to the power x, like this. We said that this was equal to 2 to the negative 1 to the power x, which is 2 to the negative x. which was the exponential function flipped, because this negative is with this x, flipped along the y-axis. And you can see that the original exponential function, let me just draw it right here. It looked like this, something like that. So if we take the mirror image, we get this green graph. And it happens that this red graph is the mirror image of the logarithm where the a was greater than 1. So you can say the same things about this logarithm. You can say the domain, the range, which you see the domain is still 0 to infinity. And also the range is negative infinity to positive infinity. You still have the same vertical asymptote as x is equal to 0. This is a one-to-one function, and it's decreasing. Okay, so that's just the basics of these types of graphs. So at least we have an idea of what it looks like. We can also talk about transformations of graphs. So when we studied parent functions, we had to move graphs around. We would have to do that for logarithms as well. So I want to do one example of that just so that we have it. So let's graph the function y is equal to log base 5 of x plus 2 minus 3. So how do we graph something like this? Well, we try to find the parent function. The parent function, so the function that gives us the idea of what this graph looks like, is y is equal to log base 5 of x. Now, this number, this base 5, is greater than 1. So this takes that form that goes through the point 1, 0, goes up like this, and goes down like this, as we mentioned earlier. This point here is 1, 0. Again, you can plug in 1 in here, and you can see that this logarithm will be 0. So how do we change this graph here to look like this one? Well, what I do is I call this a new function. I say this is, let's say this is f1 of x. And then I start playing with this to see how I can make it look like this one. So the first thing I notice is I need a plus 2 inside that log. So I take f1 and I plug in x plus 2. And this is going to be a new graph. And that's going to be equal to log base 5 of x plus 2. And when I have the plus 2 on the inside, that corresponds to moving the graph to the left 2 units. So we're just going to count over 1, 2. So this 1, 0 now became negative 1, 0. And then we're going to draw this portion of the graph is going to look very similar. And then this vertical asymptote, which is x is equal to 0, will move over 2 units to x is equal to negative 2. You might even want to draw a dotted line there to help you graph this. Like that. And then you just bring this portion of the graph down towards that asymptote. I went a little too close to it. Something like that. And then erase that graph. Okay. And then what do we need to do to this graph to make it look like the graph we want? Well, we need to subtract 3. So then what I do is I define a new function f3 of x, and that's going to be this function f2 of x. But what I'm going to do to this function is I'm going to subtract 3. And when I subtract 3 on the outside of the function, I move the graph down 3 units. So I'm going to take this point and go down 1, 2, 3 to here. This is negative 1, negative 3. And then just try to make this graph look about the same. So I did something like that. Remember, this is just a sketch. It gives me a good idea of like what the domain, the range is, and things like that. Now, I do want to write out what the domain is. So let's, by the way, this last function, f3 of x, is this function y, because if I subtract 3, I get log base 5 of x plus 2 minus 3, which is the original function that I wanted to graph. So this function of f3 of x is actually the function y. So I'm done. I don't have to do anything else to graph this. But what I want to do is I want to talk about the domain. So what can we say about the domain? Well, looking at the graph, you can see that we have this vertical asymptote at negative 2, So this is -2 to infinity. But actually, I can tell the domain just by looking at this function here. Because for a logarithm, you can never plug in negative numbers. This is really important. So let's write this down here. You can never plug in negative numbers into a logarithm. Let's verify that real quick. So let's say we wanted to take log base 2 of something negative, like -3. What does that equal to? Well, what we're asking is 2 to what power is equal to -3? Now remember the exponential function. If you plug in 0 here, 2 to the power 0 gives you 1. If you plug anything positive in here, like 2, 4, 6, 8, you're multiplying 2 with itself several times, and that's going to give you a positive number. So if you put a 2, you get 2 times 2, which is 4. If you put a 3, you get 2 times 2 times 2, which is 8, and so on. If you plug something negative in here, like a -1, well, then you just push it to the denominator. So if it was -1, you'd get 1 over 2. If you put in 2 to the -2, this is 1 over 2 squared, which is 1 over 4. In fact, any negative number you put in, you can just move it to the denominator. You will never get a negative number. So you can't plug in a negative number into a logarithm. And that makes sense because we had this vertical asymptote when we had just a regular log. So I mentioned that you could just look at the function and figure out the domain. So let's look at our function here. Let's get rid of that. So our function right here, this piece, x plus 2, has to be greater than 0. So that means x has to be greater than -2, which is the domain we got by looking at the picture. So when I ask you what the domain of a logarithm is, you're going to look at whatever's inside this logarithm, in this piece. And then you're going to set that greater than 0. So remember, when we were asked to find domains of functions, we had situations where, like if we had f of x is equal to 1 over x. Well, we said we can't divide by 0, so x can't be 0. And then if we had something like f of x is equal to the square root of x, then we said, well, x has to be greater than or equal to 0, because we can't plug anything negative in there unless we're dealing with complex numbers. But if you have something like this, where you have log base something of x, now you have a new rule that whatever's here has to be strictly greater than 0. It can't be equal to 0, okay? Because you're never going to get 0 as a you're never going to be able to get 0 when you put it in here. So for example, if you did like log base 5 of 0, this is 5 to what power gives you 0, and there's no way to get 0. Okay, so this is another domain you have to memorize. And just like before, if I put x plus 2 here, I'd have to set x plus 2 greater than or equal to 0 and solve for x. If you put x plus 2 here, you'd have to move the 2 to the other side, just like before.